Now we're ready to do our two last problems. This is one that we did in class, but I'm going to go through it again a little bit more carefully. This is the collision of two lumps of putty, and specifically, this is as observed from the center of mass frame. That means that I, as an observer, and am in a frame of reference where the one lump of putty and the other lump of putty are traveling towards each other at equal and opposite speeds, so that their net momentum is zero. And again, three momentum is conserved so that after the collision, the new blob, the super blob consisting of the putty from both blobs of putty, that is also going to be at rest in my reference frame. Okay, and that's the thing to bear in mind when we're working on this problem. Now, conservation of momentum here is trivial. Our momentum is going to be 3/5 mc in one direction and minus 3/5 mc in the other, so it's going to be 0. And that means that also our momentum is going to be 0 after the collision. And this is an important observation because it means that whatever our energy is before the collision, that is going to equal the mc squared of this blob at the end, because this blob has no momentum, and so its energy is just equal to its mass times c squared. Just bear that in mind. Let's get to work. So to calculate energy, we want to use the formula that expresses energy in terms of rest mass and velocity, because we know velocity and rest mass. So we have the energy divided by the square root of 1 minus 3/5 squared, and we get that the energy of one blob of putty is 5/4 mc squared, where the lowercase m is the mass of that blob of putty. Since, of course, we have two blobs of putty, the energies add together, and we get 5/4 plus 5/4 mc squared. In other words, our total energy of the two blobs of putty is going to be 5/2 mc squared. Now, of course, the final lump of putty is stationary, so gamma equals 1, which means that the energy is equal to the mass of the blob of putty times c squared. Now, that being the case, since mass energy is conserved, the energy before, which is 5/2 mc squared, where m is the mass of each blob of putty, that's going to be equal to capital MC squared, which is the mass of the final blob of putty. Now, the implications of this are really interesting because it means that the mass of the final blob of putty, which your intuition, thinking non-relativistically, should be 2m, because I have one blob of putty with a mass m and another blob of putty with a mass lowercase m. Combined, I would expect it to be 2m, but it actually turns out to be 5/2 m, 2.5 m. In other words, the mass of the combined blob of putty is larger than the masses of the two constituent blobs of putty that collided to form it. And this is very counterintuitive, but this is exactly where relativity challenges our intuition. Because one of the ideas of relativity, and I admit so far in going over these notes with you, I've been using this term, and I don't even know that I fully defined it for you, but mass energy is a single quantity now. There isn't conservation of mass and conservation of energy. There is a single quantity called the mass energy of the system, and that is conserved. And it also means that you can swap between mass and energy. The famous canonical example being that when you have a nuclear decay, some of the mass of the initial nucleus before it split is actually converted into the energy of the particles from the split. And in fact, because of that factor of c squared, it doesn't take a lot of mass to release a tremendous amount of energy. This is the idea behind nuclear reactors and the nuclear bomb. But the reverse is also true, and that's what we're seeing here. We have two blobs of putty that have masses of lowercase m, but that have a lot of energy because they're traveling at 3/5 the speed of light. When they collide, that energy itself transforms into the new mass of the blob. Now, there's a way of kind of thinking about this phenomenologically, or kind of a physical description of how this works. And it is that when these two putty pieces collide with each other, it's an inelastic collision. And this is no different from your intuition from physics one, which is that when you have an inelastic collision between two pieces of putty, the pieces of putty actually absorb energy, and it actually warms them up. This is the famous, heating a chicken by slapping it a bunch of times. The actual collision increases the thermal energy of these two blobs of putty, and the new blob of putty is super hot. It's so hot that all of the constituent atoms in it are moving much, much, much faster. They are moving so fast that the energy of their motion manifests itself as extra mass. And this is a common thing that can happen. In fact, the proton, very important particle for our life and world we live in, almost half of its mass about comes from the energy of its constituent particles. Another way of saying it is that its effective mass is double the mass of its constituent parts. So this is a real and a very important fact of nature, that Einstein's theory of relativity, in its beautiful way, that it sort of started from extending E and M, but then graduated to describing kinematics. It allowed us to all of a sudden understand these really, really deep ideas that under extreme circumstances, like the strong force binding the quarks of a proton together, or collisions at the speed of light, that under these extreme conditions, matter and energy are swappable between each other. Okay. Now, that is part A of this problem. And in that part, we as the observers were in the center of mass frame, meaning that the two particles were colliding, uh, and we were in a reference frame where each of them was moving in an equal and opposite direction so that their net momentum was zero. But just to show you how effective relativity is in describing many different perspectives, and showing the commonality between those different frames of reference, we're going to solve this problem in a different frame of reference. This time, the two lumps are traveling towards each other. Let me go to this diagram here where I passed it, didn't I? Yeah, the two lumps are traveling towards each other, but we're going to be in a frame of reference where we're sitting on this mass. So from our frame of reference, this mass is stationary, and this mass is barreling towards us. And I'm going to show that even though a lot of the particularities of the problem are very different from this frame of reference, the ultimate outcome is going to be the same. We're going to agree on the ultimate outcome. Okay? So let's do it. In the case where we are sitting on the left blob of putty, because the blob of putty is stationary relative to us, and therefore its momentum is zero, and its energy is just going to be, well, gamma mc squared. Gamma is 1, so again, we're just going to get E equals mc squared, where m is the rest mass of that blob of putty. And that's it. That was an easy one. Okay, now the right blob is a little bit more complicated. Its energy is going to be gamma mc squared, and its momentum is going to be equal to E squared over c squared minus m squared c squared. Now, this is a universally true formula. You can actually take the fact that the energy is equal to gamma mc squared, and you can take this energy squared and take out a factor of gamma squared, and you get gamma squared mc squared, and then we have a 1 times mc squared here. So you can write this as gamma squared minus 1 m squared c squared. Okay? So we're just using this relationship and plugging it into here, and then factoring out this gamma squared minus 1. And you can rewrite this as mc, the rest momentum, or sorry, the mass of the particle times c times the gamma squared minus 1. Okay, so the relative velocity of the right lump, it can be derived using velocity addition formula. And this is a great example of velocity addition, right? Because if you're on a blob of putty that's going at 3/5 the speed of light, and the other blob of putty is coming towards you at 3/5 the speed of light, If you were to do straight vector addition or velocity addition, Galilean velocity addition, you get 6/5 the speed of light, which of course is faster than the speed of light, which is impossible. But the correct formula for velocity addition is the sum, which goes in the numerator, and you get the 6/5. But then the denominator is 1 plus v1 times v2, which is 1 plus 9/25. And when we work this out, we get 30/34, or 88.2% the speed of light. So if two blobs of putty are each coming at each other at 3/5 the speed of light, if you're sitting on one of the blobs, then you're going to see the other blob coming at you at 88% the speed of light. And if we plug this in and calculate our gamma, we get that gamma equals 2.125. So now, what is the energy of the right blob of putty? It's going to be gamma mc squared, which is 2.125 mc squared. What is the momentum of the putty on the right? It's going to be mc times gamma squared minus 1, which works out to be 1.875 mc. And now, what's the total energy? It's going to be the left plus the right. And the left putty is just mc squared, since we're at rest in its reference frame. And the right blob of putty is going to be 2.25 mc squared. And you add that together and you get 3.125 mc squared. What's the total momentum? Well, p left plus p right is going to be 0 for the left one, because we're at rest with it, plus that 1.875, and we get 1.875 mc. Okay, so in this particular frame of reference, our total energy is 3.125 mc squared, and our total momentum is 1.875 mc. I will point out that that's different than the earlier problem, where our total energy was 5/4 mc squared, and our total momentum was 0. So we have a different combination of energy and momentum. But here's the cool part. If you take this energy and this momentum and you square the momentum and subtract e squared over c squared, you'll get mc squared. And indeed, you take that 3.125 m squared, or mc squared, and square it, minus 1.875 mc squared. Um, uh, you get what I'm saying. I'm getting tongue twisted. You square this, then you end up with 2.5 m, which is 5 halves m. And so again, oh, and that should be lowercase m here. That's a mistake. I'm having a little trouble. Bear with me. There we go. And I need the way I wrote this. Our capital MC squared is going to be equal to 5 halves lowercase mc squared. This is exactly the same conclusion we came to in the other variation on the problem. So you could see that we were able to solve this problem from a completely different perspective, and yet we got the same invariant. This is a good way to think about and practice doing problems, and I highly suggest, again, that you look at the homework problems very carefully, and really just try to look at some relativity problems where you move from one frame of reference to the other. It's not even that hard to construct problems like this, but it's really good to practice understanding, okay, who's the observer? What frame of reference is the observer in? What are the actors, what are the particles in that problem doing relative to the frame of reference that the observer is in? And then what's the total energy and momentum before and after the collision? And yeah, and then what are the invariants? So I hope these problems, you find them fairly helpful. And like I said, this is the sort of thing that I'd love for you to walk away from this class being able to do. And so practicing these for the final would be a prudent idea. Anyway, thank you very much.